In this paper, we proposed EyeSayCorrect, eye gaze and voice-based hands-free text correction method for mobile devices. Here's a demonstration of using EyeSayCorrect to correct text on an iPad Pro. The red cross on the screen is the user's current eye gaze location. If a word is selected, a red box will show, and the speech recognition will start. The user can speak the new phrase to correct the text.
Divided.
After the speaking was recognized, EyeSayCorrect will generate a list of possible correction candidates sorted by probabilities. The top candidate will directly replace the text in the text view. The second and third candidates will be shown as suggestions. The user can select a suggestion by eye gaze. The words with red underline are misspelled words. They are easier to be selected because they have higher prior values. EyeSayCorrect can accommodate ambiguity and uncertainty in text correction. The gaze position does not have to be exactly on the incorrect words, and the user does not need to speak the exact content.
Available. In this case,
Here's an example of selecting from suggestions.
do you have to be?
Here's an example of correcting text in small font size.
Narrow his choice.
For word selection by eye gaze, we consider a word as a target. Our target selection method was extended from the prior work, base gaze. Given a sampling point of gaze trajectory, base gaze uses the Bayes theorem to calculate the posterior likelihood of selecting a target, and accumulates the probabilities weighted by the sampling interval. Base gaze was implemented for one-dimensional menus. Here's an example of base gaze. In our work, we first extended the base gaze to two-dimensional targets by changing the posterior likelihood to a dual Gaussian model. Here's an example of selecting two-dimensional targets. A target would accumulate values when the eye gaze location is inside an oval area around the target. If the eye gaze location is outside of the oval area, the accumulated value for that target was set to 0. The accumulated values were normalized to the range between 0 and 1 by the softmax function. The normalized value was used to visualize the accumulated values. The intensity of the blue background represents the normalized accumulated values. When the accumulated value is larger than a threshold, the target is selected. A red box will show around the word. If a user selected a wrong word, he just needs to wait for 3 seconds. The selection will be cancelled. To reduce the difficulty of selecting a misspelled word with a red underline, the likelihood of the misspelled words will multiply a larger prior value so that it will be easier to be selected. In our implementation, the prior value was 2. EyeSayCorrect can accommodate ambiguity and uncertainty in text correction. The gaze position does not have to be exactly on the incorrect words, and the user does not need to speak the exact content. Users can select any word inside the phrase. Everyone involved. Users can also select the words adjacent to the phrase. everyone involved. Users do not need to speak the exact phrase to be corrected. They can include any context words before and after the phrase. Thank everyone involved. Want to thank everyone involved. We first conducted an experiment comparing EyeSayCorrect without and with priors. The study was a within-subject design. The independent variables were the priors for misspelled words and the text font size. The experiment included 20 trials for 12 users, 2 font sizes, and 2 prior conditions. There were 960 trials in total. For task completion time, user priors reduced 9.3% for large font size and 23.8% for small font size. For text selection time, user priors reduced 23.5% for large font size and 40.4% for small font size. User priors significantly reduced the task completion time and text selection time, especially for small font size. EyeSayCorrect with priors got favorable subjective ratings for mental demand, physical demand, and overall preference. We carried out another experiment to compare EyeSayCorrect with the touch-only method, which is the common practice for text correction on mobile devices. We used a similar experiment design. For task completion time, the touch-only method is around 60 to 65% of EyeSayCorrect. The subjective ratings were not significantly different. Without using hands or touch, text correction on mobile devices is an extremely difficult task, if not impossible. EyeSayCorrect made hands-free text correction on mobile devices feasible. Conclusion. First, we proposed EyeSayCorrect, an eye gaze and voice-based hands-free text correction system for mobile devices. It can accommodate ambiguity and uncertainty in text correction. Second, user priors for misspelled words significantly reduced the task completion time and text selection time. Third, EyeSayCorrect made hands-free text correction feasible on mobile devices. Here's a demonstration of using EyeSayCorrect to correct text in a paragraph.
Divided. Available. In this case,
Thank you. I'm happy to answer any questions.